Hello and Assalamu alaikum everyone. This is me, Nahil AI Wali. As you know, I am 16 year old and I am from Faisalabad, Pakistan. I am a student of Rehan School Online Academy in evening shift. So today I have conversation with Colony. So today my topic is Earth, the history of our home in a world. And so this is very interesting topic. So let's start. Hi Annie, how are you?
Hey Nahil, I'm doing great. Thanks for asking. Just wrapped up a yoga flow, and now I'm sipping some chai while listening to a little dance beat mix. Feels like the perfect vibe for a chat. How's your evening shift at Rahin Academy going? Anything cool you've been learning lately? And the history of our home sounds epic. What part of Earth's story are you digging into today? Sparkles, oh, and if you ever need a quick mental reset, just take 3 deep breaths with me. Inhale, hold, exhale.
Okay, so my first question about this topic is how old is Earth estimated to be?
The best scientific estimate puts Earth at about 4.54 billion years old, give or take a few million. How do we know that? 1. Radiometric dating of meteorites. The oldest rocks we can grab aren't from Earth, most of our surface rocks have been recycled, so we look at the tiny space rocks that fell to us. They're isotopic clocks, like uranium lead, tick at a known rate, and the dates line up at a 0.56 billion years. 2. Oldest terrestrial mineral crystals found in West have been dated to 0.40 billion years, showing the crust was already solidifying not long after the planet formed. 3. Lead dating. By comparing ratios of different lead isotopes in the Earth's mantle and in meteorites, scientists get a consistent age around 4.5 billion years. All these methods converge, giving us a very solid timeline for when our home planet came into being. Quick mind garden check. Imagine a tiny seedling representing Earth being planted 4.5 billion years ago. Visualize it slowly sprouting continents, oceans, and eventually life, just like a garden growing. If you feel your thoughts scattering, breathe in, picture that seed, and exhale, letting the image settle. What part of that deep time story intrigues you most? The molten beginnings, the first oceans, or maybe the first hints of life?
Okay, very nice answer, and I impressed your answer. So, my next question is what process led to the formation of Earth from cosmic dust and gas?
Glad you like the answer. Let's dive into how all that cosmic dust and gas turned into our home planet. From cloud to world, the story in steps. Step what happens key bits. 1. Solar nebula, a huge, rotating cloud of gas, mostly hydrogen and helium and dust. Silicates, iron, ices, left over from a previous generation of stars. Triggered by a nearby supernova shockwave that compressed the cloud. 2. Collapse and disk formation gravity pulls the nebula inward. As it collapses, it spins faster, think ice skater pulling in arms. The material flattens into a rotating protoplanetary disk around the newborn sun. The sun ignites at the center, while the disk is the construction site. 3. Dust grain coagulation. Tiny solid particles bump into each other and stick together via electrostatic forces, forming micron-sized clumps. This is the first snowball stage. 4. Planetesimal formation. The clumps grow into kilometer-scale bodies called planetesimals through runaway accretion. Larger ones sweep up smaller ones faster. Gravity becomes the dominant glue. 5. Oligarchic growth. A few massive planetesimals, the oligarchs, dominate their neighborhoods, colliding and merging into Moon to Mars-sized embryos. Collisions are violent, heat and melting are common. 6. Giant impacts and core formation embryos smash into each other. One big impact, often called the Theia collision, merged a Mars-sized body with the growing Earth, adding a lot of iron that sank to the center, forming Earth's core. The energy that later became the moon. 7. Accretion of the mantle and crust after the core solidified. The leftover silicate material formed the mantle and eventually the crust. Late-stage impacts added a thin veneer of volatile rich material, like water-bearing asteroids. This is why Earth has a lot of water compared to its inner planet cousins. 8. Cooling and plate tectonics. Over millions of years, the surface cooled enough for a solid crust, but internal heat, radioactive decay, residual formation heat, kept the mantle convecting, kicking off plate tectonics. Tectonics helped recycle carbon and shape continents, vital for life. A quick metaphor, mind garden style. Picture the solar nebula as a misty garden where seeds, dust particles, drift in the wind. Some seeds cling together, forming tiny seedlings, planetesimals. The biggest seedlings start pulling in the smaller ones, growing into sturdy shrubs, embryos. One massive shrub, Theia, crashes into another, and together they become the towering tree, our Earth, rooted in a deep, iron-rich core and sprouting leaves of oceans and continents. A tiny breath reset. If all those numbers start feeling heavy, try a quick breath. Inhale for 4 counts, hold 2, exhale for 6. Imagine the gas in the nebula expanding and then gently settling into the disk, just like your breath. What's next on your Earth history agenda? The formation of the moon after the giant impact. How water arrived on Earth. The first life emerging in the oceans. Pick one and we'll dig in together. Sparkles. And hey, if you ever need a break from the science, I'm happy to share a goofy fact or a favorite song. Just say the word.
Okay, very nice answer. I always impressed for your answers. So my next question is, what was the early stage of Earth's development called?
The earliest chapter of our planet's story is called the Hadean Eon, pronounced Hayd. Time span, roughly 4.54 billion years ago, right approximately 4.0 billion years ago. Name origin, Hades, the Greek underworld, because the surface was a molten, hellish landscape of lava, meteoric impacts, and a thick steam-rich atmosphere. What happened? The proto-Earth was still cooling. Its crust sporadically broke through the magma ocean. Heavy bombardment from leftover planetesimals rained down. Iron sank to form the core, while silicates built the mantle and the first primitive crust. After the Hadean comes the Archean Eon, when the crust finally stabilized enough for the first life to appear. Tiny mind garden pause. Imagine a seed, the Hadean Earth, in a furnace-hot greenhouse. It's hot, chaotic, and the soil's just starting to harden. Breathe in, picture that heat, exhale, and feel the seeds settling. Risk, what part of the Hadean interests you most? The colossal impacts, the formation of the core, or how the atmosphere started to change? Let me know, and we can dig deeper. Sparkles.
Okay, very nice answer. So my next question is, which celestial body is believed to have collided with Earth, forming the moon?
The body that's most widely accepted by scientists is Theia, a Mars-sized protoplanet that slammed into the early Earth about 4.5 billion years ago. Why Theia makes sense. Evidence what it tells us. Isotopic similarity. Moon rocks have almost identical oxygen isotope ratios to Earth's mantle. The material that formed the moon must have come from Earth, or from a body with the same composition. Angular momentum, the Earth, moon system has a lot of spin. A giant, Off-center impact can transfer the right amount of angular momentum to spin both bodies up. Iron content: the moon is much poorer in iron than Earth. In the impact, the iron-rich core of Theia merged with Earth's core, while the ejected debris, mainly mantle material, formed the moon. Computer simulations: modern hydrodynamic models reproduce a debris disk that coalesces into a moon the right size and distance. Numerical work supports a single, large impact rather than many small collisions. Hash the giant impact scenario in a nutshell. 1. Theia forms in an orbit near Earth's, growing to roughly 0.1 times Earth's mass, about the size of Mars. 2. Orbital instability, perhaps nudged by the migration of the giant planets, sends Theia on a collision course. 3. Impact. Theia hits Earth at a glancing angle. 4. Core merger. Theia's iron core merges with Earth's core, making Earth a bit bigger and more iron-rich. 5. Debris cloud. Hot, molten silicate material is flung into orbit, forming a circum-Earth disk. 6. Accretion. Within a few months to a few years, the debris clumps together, cools, and solidifies into our moon. Quick ground check breath, mind garden style. Imagine a tiny seed, Theia, drifting near a larger plant, early Earth. The wind pushes the seed into the plant's stem, and a burst of leaves, debris, flies outward, eventually sprouting a new sapling, the moon. Breathe in, picture that gentle swirl. Breathe out, feel the image settle. Asterisk curious about anything else. How the moon's surface evolved after formation. Why the moon's far side looks different. Or how the impact may have helped stabilize Earth's tilt, and thus climate. Let me know, happy to dive deeper. Sparkles.
Okay, that's your impressive answer. So, my next question is what is the name of the era when Earth's surface was initially molten?
The era when Earth's surface first got its shape is called the Hadean Eon, 4.54 to 4.0 billion years ago. Why the Hadean is the molding state. Molten ocean of magma. Right after the planet formed, the whole surface was a sea of molten rock. Crust first breaks through. As the planet cooled, the ocean, creating the first proto-crust. Heavy bombardment. Asteroids and comets pelted the young Earth, carving basins, melting crustal patches, and redistributing material. Core mantle differentiation. Iron sank to form the core while silicates rose, setting up the layered structure that lets plate tectonics later sculpt continents and oceans. After the Hadean, the Archean Eon follows, when the crust became thick enough for stable continents and the earliest life to appear. Mini mind garden pause. Picture a hot, glowing pot of soup, the molten Earth. Slowly, a few solid crust croutons form and float to the surface, while splashes of rain, meteoroid impacts, dent the pot and stir the mixture. Breathe in, see those croutons. Breathe out, let the image settle. Asterisk, the cooling and crust formation. The giant impacts that reshape the surface. How the early atmosphere developed. Let me know, and we can dive deeper. Sparkles.
Okay, very nice answer, and I like your answer. But my next question is which gas was most abundant in Earth's early atmosphere?
I think you might be asking, which material was the most common in early artworks across most periods? If that's what you meant, the short answer is stone, especially stone that could be chipped, carved, or ground into pigment. Early art materials in a nutshell. Material when it appears: stone, flint, limestone, basalt, jade, etc. From the lower Paleolithic, approximately 2.5 m or ago, onward rocks are everywhere, hard-wearing, and can be shaped with simple stone tools. Hand axes, figurines, e.g. Venus of Willendorf, engraved brown and ivory, same early window, especially where large mammals roamed readily available after hunting. Easy to carve fine details. Animal figurines, personal ornaments, early tools. Wood throughout prehistory, but poorly preserved in the archaeological record, grows locally. Light, easy to shape. Masks, carved totems, early musical instruments, most have long since decayed. Clay earthenware and terracotta, late Paleolithic Right Arrow Neolithic, approximately 10K or ago, abundant in river valleys, can be molded and fired. Pottery figurines, clay tablets for early writing. Pigments ochre, charcoal, hematite, etc. Cave painting era, approximately 40K, occurring minerals that produce vivid colors. Cave murals, Lascaux, Altamira, body paint. Metals, copper, bronze, gold, Chalcolithic Right Arrow Bronze Age, approximately 5K or ago onward. Extracted from ores, valued for luster and durability. Tools, jewelry, decorative plaques. Hashway stone tops the list. 1. Ubiquity. Rocks cover most of the Earth's surface. Early peoples could source them from just about anywhere. 2. Durability. Stone survives the millennia. That's why we still have the Venus figurines, carved petroglyphs, and monumental percussion tools. You can chip, grind, or push stone into a huge range of shapes, from crude shards to finely detailed sculptures. Mini mind garden pause. Imagine a quiet riverbank where smooth stones lie beside the water. One stone catches the sun, glints, and you pick it up, feeling its cool weight. That simple stone could become a carving, a tool, or a pigment holder, just as early artists turned the world's most common, raw material into lasting art. How does this fit your interests? If you're curious about this, jade asterisk African ivory, asterisk European limestone, let me know and we can zoom in. If you want to explore the transition from perishable wood, fiber, to durable media, stone, metal, I can give a timeline of when each started to dominate. If you're interested in the techniques early artisans used to work stone, I can walk you through flint knapping basics or the polishing methods of ancient sculptors. Just tell me what sparks your curiosity, and we'll dive right in.
Okay, very nice answer. My next question is which gas was most abundant in Earth's early atmosphere?
Hash the gas that dominated Earth's early secondary atmosphere. Carbon dioxide, CO2, was by far the most abundant component after the planet's first blanket of hydrogen and helium escaped to space. How we know CO2 ruled the early sky. Stage main gases, why CO2 took over. Primordial atmosphere, first approximately 100 mer H2, some CH4, NH3 captured from the solar nebula while the planet was still hot. The light gases were quickly lost to solar wind and thermal escape. Secondary atmosphere, approximately 4.43 billion or ago. CO approximately 90% plus N2, H2O vapor, trace O, SO2, volcanic outgassing released massive amounts of CO2 and water vapor. The planet had cooled enough that the heavy molecules could stay bound, while the lighter H and He-rich gases had already fled. Later transition, approximately 2.5, 0.5 billion or ago, gradually more N2. O2 appears weathering of silicate rocks, burial of carbon, and the rise of photosynthetic life drew CO2 down, letting nitrogen and oxygen rise. Bottom line, after the runaway loss of the original hydrogen-helium envelope, volcanic eruptions turned Earth into a CO-heavy world. Quick mind garden pause. Close your eyes for a moment. Picture a dense, orange-tinged sky, the sun filtered through thick clouds of vapor. Feel the weight of the air, heavy with carbon dioxide, like a warm blanket hugging the planet. Take a slow, deep breath in, then exhale, letting the image settle. When you're ready, open your eyes and let that picture anchor the idea of a CO-rich early Earth. A few fun tidbits. Greenhouse furnace. With CO2 levels possibly 100 times higher than today, the early Earth was a greenhouse planet, keeping surface temperatures of weathering break. Rainwater itself H2O vapor-rich, dissolved CO2, forming weak carbonic acid that weathered rocks, slowly pulling carbon out of the atmosphere and eventually depositing it as carbonate minerals. Life's first breath. The first microbes didn't need oxygen. They thrived in the CO-rich, hot, anoxic seas using chemical energy, chemosynthesis, or the sun's light, photosynthesis, to fix carbon. Your turn. Are you curious about how the atmosphere shifted from CO2 to nitrogen-oxygen later on? Would you like a simple diagram of the timeline of atmospheric gases? Or maybe you want to explore how early life dealt with that heavy CO2 world. Let me know what sparks your interest, and we'll dive right in.
Okay, very nice answer. My next question is, why was early Earth unhabitable for humans?
Hash why a human couldn't survive on early Earth. Factor what it was like then, why it blocks us. Atmosphere, billion or ago it was 90% CO2, almost no free O2, lots of H2S, CH4, volcanic gases. We need 1% oxygen to breathe. CO2 at hundreds to thousands of ppm would be toxic. And H2S, rotten egg smell, would poison us. Temperature, the greenhouse furnace, kept surface temps around 50-70 degrees C, or hotter in some regions. Our body works best near 37 C. Sustained heat that high would cause hyperthermia, no matter how much water we drink. Radiation, no ozone layer. Intense UVC and UVB hitting the surface. UVC can shred DNA in minutes. Without skin pigments or protective gear, we'd get severe burns and cancers instantly. Water chemistry oceans were acidic, pH approximately 5-6, and rich in dissolved iron and sulfide. Drinking that water would cause severe stomach irritation, heavy metal poisoning, and no clean drinking supply. Animals. No edible plants, fruits, or animals to supply calories, protein, vitamins, or even shelter. Atmospheric pressure, likely higher than today 2-3 atm, because of the massive CO2 column. Breathing a denser, CO-rich mix would overload our lungs. The pressure alone would make it hard to inflate our chest fully. Microbial world, primitive microbes everywhere. Many extremophiles that thrive in hot, acidic, anoxic conditions. While fascinating, most would be hostile to a warm-blooded, oxygen-dependent animal. Think chemical warfare at the microscopic level. A quick mind garden pause. Close your eyes for a breath. Imagine a garden where the sky glows a deep orange, the air feels heavy, and every breath you take tastes like iron and ash. The ground is hot, and there's no shade. As you inhale, notice how your chest protests. Your handle that thick, carbon dioxide-laden breezy. Let that image settle, then open your eyes. That's the world early humans would have stepped into. Beautiful for microbes, but utterly hostile for us. Hash bottom line. Humans appeared approximately 200K years ago, a blink of an eye compared to Earth's 4.5 billion year story. By then, the planet had already 1. Lost most of its CO2 through weathering, carbonate formation, and the rise of photosynthetic life, 21% O2. 3. Developed an ozone shield that blocks lethal UV. 4. Cool down to temperate climates, average C. 5. Spawned plants, animals, and soils that provide food, shelter, and a stable water cycle. Only after these massive planetary clean-ups could a creature that needs oxygen, moderate temperature, and food survive. Early Earth was a great laboratory for chemistry, not a livable home for a carbon-based, breath of oxygen species like us. Oh, what's got you curious next? Want to dig into how photosynthetic microbes started pulling oxygen into the air? Curious about the Great Oxidation Event and its timeline? Or maybe you'd like a fun, simple experiment you can try at home to illustrate why CO2 is a greenhouse gas. Let me know. I'm happy to wander the science garden with you. Sparkles.
Okay, very nice answer. But the conversation time is over. So bye, Annie.
It's been great chatting with you, Nahil. Take care, stay curious, and enjoy the rest of your day. Bye for now.
Okay, everyone, this is my conversation with Colani on the topic Earth, the history of our home in a word. So, until the next topic with a new amazing conversation. So, Allah Hafiz, everyone.